So, hello, welcome back to this series of lectures on combustion in scramjet engines. Now, as we have discussed in the introductory lecture itself, one of the biggest reasons why combustion is used in air breathing propulsion is because of the high energy density of the liquid fuels. So, in any propulsion device that you see, in any air breathing propulsion engine that you see, whether it is gas turbine engine, ramjet, scramjet engine, the ultimate motivation is to use liquid fuels, okay, because of the very large energy density that it provides. So, similar thing in scramjets also. So far in the previous class we have discussed how the jet trajectory can depend on the dynamic pressure ratios when we used gaseous fuels. Of course, scramjets there has been many instances where gaseous fuel has been used. For example, the X-43 series of scramjets that was designed by NASA and Boeing that used gaseous hydrogen. Of course, the reason was that with gaseous hydrogen is much easier to ignite, and quickly it mixes because there is no such process as like liquid jet breakup atomization, which are inherent in liquid fuels. But then because of the energy density because of the high energy density of the liquid fuels, if scramjets has to evolve as commercial propulsion engines, probably it will move in the direction of liquid fuels. Okay. So, that is why it is very important to analyze or examine the feasibility of using liquid fuels in scramjet engines. Okay. So, how do you inject liquid fuels inside a scramjet engines? Of course, one of the ways is to inject it as a transverse jet. That is, suppose you have this as the scramjet engine like this, and you and from here, so you have the Mach 2 flow entering into the combustor. So, perpendicular to the airflow direction, you inject a liquid jet. Okay. So, of course, now the liquid jet and the supersonic airflow, okay, because the airflow has to be supersonic because it is a scramjet. So, now the liquid jet and the supersonic airflow will interact in a very complicated manner, and lot of research effort is underway to understand what are the different instabilities that develop on the surface of the liquid column. And these instabilities are important to understand because ultimately these will lead to the jet breakup, and the air shear will can lead to atomization, and then of course once droplets are small enough they can evaporate, and this after evaporation the liquid the fuel can mix with the air. Okay. So, this is the whole thing. It is very important thus to understand how a liquid jet essentially breaks up and atomizes in a supersonic cross flow. Okay. Now, what are the important parameters? What does what does the past research suggest? The past research suggests that the most important parameter that controls the behavior of the jet of the liquid jet, where it will go, how it will break up, how it will atomize, and eventually the combustion properties, the entailing combustion properties, those is governed in this case also by the dynamic pressure ratio. Okay. So, the dynamic pressure ratio once again is a very key parameter. Of course, you see that in the dynamic pressure ratio your momentum is also included. Okay. So, it is a static pressure plus is a P plus rho u square, that is the essentially the included in the dynamic pressure ratio. Okay. So, this is both the static pressure as well as the momentum of the jet relative to the liquid jet relative to that of the supersonic airflow is a key parameter here. Now, what research suggests is that if the DPR, that is the dynamic pressure ratio, is greater than 6, okay, that is if the liquid dynamic pressure of the liquid jet is very large compared to that of the supersonic air, then the liquid jet penetrates of course several jet diameter. That is, it's easy to understand that if this liquid jet, so suppose you are considering a scramjet and you are injecting the liquid jet here, so your Mach this is your Mark II flow. So if if the jet momentum is very high, of course it will go in a it will penetrate much deeper. If the jet momentum is weak, it will penetrate much like this. Okay, that is here of course the what I mean to say is that if the liquid jet momentum is much higher compared to this the airflow momentum, then it will proceed in this manner. If the liquid momentum is weaker compared to the airflow momentum, then it will stay close to the wall. Okay. Now, when you are designing, when you are choosing the injector and you are choosing the pressure that with which you are going to inject the liquid fuel, then it's important to understand where you want to inject your liquid fuel. Okay. Now, in certain cases you might want to inject the liquid fuel so that it goes into the main air flow. In certain cases you might have a cavity, as we will see later, you might have a cavity here. So, it might be a good idea to inject it close to the walls and allow it to stay close to the walls. So, then the idea is that then depending on your choice or where you want to put your maximum fuel, you have to choose your dynamic pressure ratio. So, what research suggests that is if the dynamic pressure ratio is greater than 6, then the liquid jet penetrates several jet diameter undisturbed, and then it begins turning. And then so it goes several jets, it goes straight into it penetrates into the several jet diameter undisturbed, and then it begins turning, and the surface waves grows leading to its breakup. Okay. So, initially if the dynamic pressure ratio is very large, initially the jet does not even feel that there is a supersonic cross flow coming, it proceeds on its own before leading to breakup. If the dynamic pressure ratio is intermediate from 1.5 to say 1.5 to 6, then large jet surface waves immediately develop and the jet breaks up within a few jet diameters. And if the DPR is less than 1.5, then the jet is abruptly turned, that is in this case, and remains a narrow layer close to the wall. So, this is the different behavior of the liquid jets. Okay. Now, what fuel do you use? Of course, one can use different kinds of fuels like JP10, JP7, etc. But here once again, if we just recap, so we discussed about jet fuels. So, jet fuels is essentially like a mix of different things. But we want to now understand the reason why we come to Jet A is that we now want to understand typically what can be the characteristic ignition delay in a scramjet engine. Okay. So, that is why let us say that if our Jet A is a choice, then we have to know that what are the basic the fundamental compositions, fundamental constituents of Jet A, and what kind of a surrogate fuel we can use to represent Jet A, and then we can find out the ignition, the 0D ignition delay for that fuel air mixture and at the scramjet relevant conditions. So, that will give us some idea about how much time does it take for ignition and whether at all it is possible to have ignition in a scramjet where we can have an approximate idea of what the flow residence time scale would be. So, what is Jet A? Jet A, as you see, is we discussed before in the kinetics class, is an average formula of about C11.37H21.87. So, we can say that, and it of course contains a lot of different kinds of paraffins, N-paraffins, isoparaffins, etc. And of course, it has some amount of aromatics also, but the rest are reasonably paraffin. So, that is why people think that n-dodecane is a good idea to is a good alkane to represent Jet A. Okay. Now, if we do that, what we see is that once again we come back to this negative temperature coefficient plot. Of course, this is at high pressure, that you must understand, but you see that around this temperature, okay, this 1000 by when 1000 by T is equal to about 1.2. Okay, so T is equal to the 1000 by 1.2. So, it comes to about the approximate scramjet static temperatures. So, in that region you see that you have this whole phenomena of negative temperature coefficient. Okay, so that is why and another important thing is that you see the whole the time scale is of the order of 1 milliseconds, okay, in this whole range. So, you have a negative temperature coefficient and your time scale is also quite large relative to the scramjet flow residence time scales. In a 1 meter long scramjet, if the flow velocity is 1 kilometers per second, okay, then your the flow residence time scale is about of the order of 1 milliseconds. So, here also from the 0D ignition delay, where you have not considered mixing, where you have not considered anything else, atomization, evaporation, anything. So, the pure ignition delay time scale for a 0D mixture where it is it's only the homogeneous mixture of n-dodecane air is undergoing auto ignition, and there itself the tau ignition is 1 milliseconds. Okay. So that is why, but you have to understand that now if you want to design a scramjet engine, or you want to predict the performance of a scramjet engine which uses kerosene as a fuel, it is imperative that we use a detailed reaction model, because this time scale of 1 milliseconds of this ignition delay and this NTC behavior that you see here, it cannot be captured by one step chemistry. So that is why in scramjet engines often it is suggested to use detailed reaction mechanisms. But of course if it is one is using very different, very reactive fuel like hydrogen, where these things are not important, so then in that case one step chemistry might be good enough. So once again, this is just we discussed this before, just a recap. So now this gives us idea of the auto ignition timescales, which is about 1 milliseconds. Now if we go to the scramjet relevant conditions, that is if we go to the temperatures which are little higher, that is in this range, okay, in this range which are more scramjet relevant conditions, so that is then this is how the temperature versus time behavior happens in an auto ignition calculation. So this is these calculations are performed using Senkin, which is one of the suite one of the models inside Chemkin for calculating the auto ignition, the ignition delay for a 0D reactor, where only where you only compute the change of temperature with the heat release along with the species equation, but there is no transport. Okay. So you see that when your T in is about T starting initial is about 1200 Kelvin, then you get get this plot of about where you get an auto ignition delay about 1.2 milliseconds, whereas if you increase it by 1300 Kelvin, then it becomes quite drastically changes, and it becomes of the order of 0.3 milliseconds. So in this range, as you see that this is at a given pressure of about 0.5 atmosphere, that this is a huge variation, right? It's a variation of from about 1.2 milliseconds to about 0.3 milliseconds, and this difference can make can render ignition possible or impossible. That is, you might have a situation where ignition is impossible, that if you are at T in equal to 1200 Kelvin, but you might have a situation where ignition is possible when you are T in is about 1300 Kelvin, because it changes by an order of magnitude in this range. It's very, very sensitive. So that is why it is important to use detailed reaction mechanisms. Typically for n-dodecane air, one uses a jet fuel mechanism, not this one. This is there is an error. One use the jet surf mechanism by the same with the same author, Hai Wang. Okay. So this is the thing that here you see the effect of pressure variation also, but that here also you see that if you go from 0.5 atmosphere to 0.9 atmosphere, okay, so so this is at 0.5 atmosphere, and this is at 0.7 atmosphere, and this is at 0.9 atmosphere. Okay. So as you increase the pressure, of course the ignition delay reduces. Okay. So the ignition delay reduces. So from about 1.25 milliseconds, it goes to about 0.9 milliseconds. But of course pressure has some effect, but it is not as sensitive as that of temperature, where you see that here with the difference, once again to recap, with a change of temperature of just 100 Kelvin. Okay. In combustion 100 Kelvin is nothing, right? So just by a change of temperature of about 100 Kelvin from 1200 to 300, your ignition delay drops by from 1.25 to essentially 0.3. So it's a factor of 4 almost drop that you get in the ignition delay. Okay. So this has to be remembered when you do this kind of calculations, and when you calculate the ignition delay time of a scramjet engine. Now burning time, that was just ignition delay time. Burning time, these are empirical correlations with which one could estimate the burning time. This is comes from the paper by Mitani, where he used the burning time. He defined it as the burning time could be defined as the time to achieve time required to achieve 95% of the equilibrium temperature. And the empirical correlations suggest that this is the time where of course it's dependent on pressure, but in a scramjet scramjet engine the pressure varies. Okay, so if you plot the distance versus pressure in a scramjet engine, you will see the pressure varies like this, whereas this is the point of the fuel injection. What he suggested is that you can define an average pressure PV, which is defined in this manner, which is an integral, which is basically some form of an averaged pressure, and this exponent n is essentially the pressure exponent that is here, and from that one gets an estimated burning time of 10 to the power minus 3 seconds, which is 1 milliseconds. So this suggests that, once again, if you recall that what I said, that in a scramjet engine, the flow residence time scale is of the order of 1 milliseconds. Okay, in a combustor it might be even smaller than that. It's of the order of that. So it might be 1 milliseconds, 2 milliseconds, 3 milliseconds to 10 milliseconds. So 1 to 10 milliseconds depending on the flow conditions. But if the burning time is of the order of 1 milliseconds, then of course you cannot expect that you can just have inject fuel into the oncoming high speed supersonic air at Mach 2 and it will burn on its own. Okay, and there we cannot have flame stabilization that way. So this calls for a need of a flame stabilizer, and in scramjets you can have either like a cavity stabilized flame or a strut stabilized flames, which will come. But before going into that, just to give you an idea of how the flame inside a scramjet look like. So when you inject the fuel, of course, as you have seen, that leads to the formation of a bow shock and surrounding the barrel shock when you inject fuel, because the fuel jet poses an obstruction. So this is a hydrogen jet injection in a cross flow of air about 2.4 at static temperature of 1400 Kelvin. This comes from the work of Gamba and Mungal, recently published. So when you inject this hydrogen jet at this point, you see this is the OH PLIF images by the same technique we described previously. So you see that this due to the high temperature of this air stream that comes here, so the flow is coming from here and you are injecting the jet here, and you see this bow shock forming, and then there's a barrel shock forming here, and of course there are like different other structures forming all throughout. Now because of this jet induces compression, and this shock induces compression, and also it induces temperature rise, and that causes immediate auto ignition. Of course the actual static temperature of the flow is also quite high, and as you see here, you see this kind of flame being forming, but the flame that you see here is a very strange looking flame. It's like this OH normally does not happen in bulk. Instead it is like it's like in a threaded form, like this. You see the flame being scattered all the way along this both in the front of the jet and as well as in the back of the jet. And people think that this can be the examples of broken reaction zone regime. These flames belong to the broken reaction zone regime of the turbulent combustion regime diagrams that we have discussed. So as such, that happens when the chemistry and when the reaction time scales are very are much larger compared to the Kolmogorov time scales. That is when you get this kind of broken reaction zones, and people think that this is probably what is happening here. Okay. Now, this, as you see, that if you just inject in this thing, you get it's very difficult to realize a robust flame. So that calls for a need of flame stabilization. So one of the flame stabilization mechanism is by using cavity. So what you have is that you have this scramjet combustor. This is, say, the isolator, and then you have the divergent section, and then you can have a cavity like this. Okay, and then the flow comes, and it essentially, as you see, it can recirculate here, and you can inject fuel into this cavity. So this is what is being shown is that, so this is the bottom wall where this boundary layer is developing, and now as the flow, this supersonic flow encounters divergence, this expansion waves form. Okay, the flow can expand, and which causes these expansion waves, and this boundary layer bends. Okay, and also between this bends into this cavity. So this is the let me just explain. So what we have is that so this cavity is represented here. Okay. So, the flow is coming from the left to the right, and it as it comes, there is a boundary layer being formed, and here you have a cavity which is formed like this. Okay. So, as the flow is coming, it encounters divergence, and when divergence, you have a divergence, you have got this expansion waves, and these expansion waves further turns the flow, and you have a boundary layer coming inside the cavity. Now, inside the cavity you do not have a direct flow, of course. So, there is a shear layer being formed because the velocities of these two, of inside cavity and outside cavity, are widely different, and then the flow essentially comes and recirculates like this. Okay. So, now in this recirculating flow, because the flow residence times are very high, you can inject a fuel. Okay. Now, you can inject a fuel, and this fuel can mix with this recirculating flow, and this can lead to combustion. And it can have a reasonably steady flame inside this cavity. So, this is one of the strategies that are being adopted inside a scramjet combustor. Okay. The advantage of this kind of a rearward phase step cavity is that that whatever the pressure rise happens, this pressure rise does not, you can essentially shield the flow from the pressure rise that happens due to combustion. And second is that the absence of intrusive devices, that if you include a flame holder, that may generate stagnation pressure loss and might require internal cooling, because this strut, if you put just like the bluff body, what we have seen before in the afterburner, that can lead to a very high that the leading edge of the strut will see temperatures which are equal to the stagnation temperature of the flow, because the flow has been stopped there. So, and if that is of the order of 1600 1700 Kelvin, for long term operation you might need some cooling. So, and also it can lead to some pressure loss. So, that is why some people prefer cavity, but the only issue is that in the cavity your combustion is restricted to the sides. So, the main flow does not see combustion. So, if you want to generate a lot of thrust by accelerating the flow, you have to somehow ensure that the main flow gets, a lot of the main flow gets into the cavity, and if you cannot have a very large divergence immediately, so then it can lead to flow separation. So, these points, there are advantages and benefits and disadvantages of cavity, but this is definitely one of the two ways by which flame is stabilized inside a scramjet combustor. So, the next one we will talk about is essentially the flame stabilization using struts. So, this work will essentially report the DLR scramjet experiments reported here by Guerra et al, and the computations have been reported by Genin and Menon in EIA 2009. So, we will just examine this as a case of how combustion, how a flame is stabilized by a strut in a scramjet type of combustor. So, here we have a Mach 2 flow coming in from the right to the left, and the temperature is 340 Kelvin. So, you need additional ignition mechanisms, and the strut is of the order of with a divergence angle of 12 degree. And now, you see here you cannot place a bluff body like what you place in an afterburner. Okay. So, because if you place a bluff body, then immediately there will be a normal shock formed, and this normal shock will make the flow downstream subsonic, and the whole thing breaks down, the whole concept of the scramjet combustor breaks down. Okay. So, you have to design this strut very carefully, and it can only have a very narrow edge angle, and it cannot always also block the flow too much. So, that needs to be carefully chosen. Okay. So, here because it will have heat release, so they had designed a combustor with a 3 degree divergence. As you see, it is not straight, it is not these the top wall and the bottom wall are not parallel. The top wall diverges at an angle of about 3 degrees, and the strut has a divergence angle of about 12 degrees, and from the center of the strut you are injecting hydrogen at Mach 1, whereas the incoming air is coming at Mach 2. Okay. So, this is how essentially the Schlierian image of this hydrogen air flame looks like, but we will go into that. So, now we have not really discussed large Jetty simulations for doing compressible reacting flows. So, in this last lecture we will just show you that this kind of complex scramjet combustors can be simulated using large Jetty simulations. Okay. So, large Jetty simulations is kind of intermediate between direct numerical simulations and RANs. So, in for example, in direct numerical simulations you solve for all scales from the combustor size to the Kolmogorov length scales. Okay. In RANs, you solve for only the average, either the arithmetically average ensemble average variables or the Favre average variables. In LES, what you do is that you solve for filtered variables. Okay. Now, in these filtered variables, what is contained is the information from the larger scales to some intermediate scales in the which belongs to the inertial range. So, these variables that you see, this all this bar and tilde, this barred variables, for example, this rho, for example, this rho bar is essentially the non-density weighted filtered variable. So, in LES, large Jetty simulation, you solve your governing equations, you create first governing equations that describes the evolution of these filtered variables, and this tilde denote the density weighted filtered variables. For example, U tilde here denotes the filtered, these are like filtered variables. Okay. So, with this you can capture large scale dynamics and have models for essentially the small Kolmogorov scales. Okay. So, this is your continuity equation once again for this filtered variable U I tilde. This is the momentum equation. You see emergence of this tau I SGS terms. These are similar to the Reynolds stress terms that you encountered in RANs, and you have to essentially model for this. So, this is your energy equation. I will not go into that, and this is your species equation. So, once again these equations look very similar to the actual governing equations, but they have many more terms. They are more complex because they have many more terms due to this subgrid scale terms that arise. Okay, that is which are like kind of this Reynolds stress terms, UI UJ term, which you remember arrived when we averaged the Reynolds the Navier-Stokes equation. Okay, similar to that, these terms arrive everywhere in this momentum equation, in this energy equation, in this species equation, and one has to have a closure model for that. For example, in this case, this tau I SGS that arrives here is closed by this eddy viscosity type of closure, and then you solve for this K SGS similar to this K epsilon model also. But this is much more involved, but it gives you much more insight. So, this is just to show that these simulations, what these simulations can do, and it can capture essentially very many of this interesting physics that is there present in these kinds of flows. So, here we are showing the density gradients that is obtained from this large Jetty simulations, and often these are close to experiments and sometimes they are not. So, still now this large Jetty simulation for high speed turbulent combustion is a research topic. A lot of advancements has been made, but it is not closed, and still there is room for a lot of work that can be done. Okay. So, both fundamentally as well as developing algorithms as well, or developing numerical schemes, and as well as in terms of fundamental understanding. So, what I want to show here is that here we compare from the solutions, we compare the density gradients from the non-reacting and the reacting flow. Of course, you see that they are different, but first if we just define the non-reacting flow part. Okay, so you see that here the supersonic flow is coming from the right, from the left to the right. Okay, and here also, as you see that the supersonic flow is coming from the left to the right. Okay, so here as it encounters, as it comes from the left to the right, here it is encountering this wedge shaped body. Okay, and as it is deflected by the tip of the wedge, you have these two shocks which are being formed. Okay, these two oblique shocks which are formed, let us call this A and let us call this B. Now, what happens is that as they impact this upper and the lower walls, they reflect back. Okay, then they reflect back towards the center line of this test section, and the impact of the shock on the upper wall occurs downstream of the location of the divergence. Okay, so you see that this wall interacts with this shock interacts with the wall after the divergence has started. So, as a result of this whole shock structure does not remain symmetric with respect to the center line anymore. Okay. So this changes the symmetry, and you see that this is this whole line, the center line of the shock structure has deviated from the center line of the from the center line of this of the constant area section. Okay. So, but you see here that what happens is that the impact of the shock on the upper wall occurs of course downstream of the location of the wall divergence, and as a consequence the oblique shocks interacts with the upper wall expansion fan that is created due to at this corners of this flame holder. So these are the expansion fans which are created because the flow is diverging. Okay. And these reflected shock structure interacts with this expansion fan, and because of this inherent asymmetry, this whole thing becomes asymmetric downstream. Okay. Now, what happens is that you see at the base of the wedge, okay, there are these boundary layers being formed, and this base of the wedge, this boundary layers are formed, but because the pressure inside the recirculation zone is lower, these boundary layers essentially these shear layers which are formed here now essentially try to converge. Okay, and then these two essentially try to converge towards the center line, and as this tries to converge towards the center line, then what happens is that because of the low pressure inside this recirculation zone, the hydrogen jet, the Mach 1 hydrogen jet that you are injecting is essentially becomes under expanded, and this forms this whole nice diamond shock patterns. Okay, and this again then pattern continues, and then this shock diamonds are essentially formed, which leads to the interaction between with the shear layers. But the most important feature here is that this low pressure inside the recirculation zone causes this the convergence of the low pressure of the recirculation zone causes the convergence of this whole of the shear layer into the towards the center line. So that is what you are seeing here. But on the other hand, when you have this when you have a reacting flow, for example in this case, here also you see that as the Mach 2 flow comes here, it is deflected indeed by the wedge. Okay, and this oblique shocks are being formed, and which again reflects back into the shear layer. But here what happens is that now, because there is combustion now, because there is now you have got heat release, the pressure inside the recirculation zone is higher. Okay, so as a result of that, since the pressure at the base of the wedge has increased, okay, as the reaction has been initiated, the shear layers do not converge anymore, but rather expand with an angle which is even slightly greater than the 12-degree angle of the wedge. Okay. So this is the striking different feature. Okay, another thing that you will see essentially in the next slide, that where we have essentially plotted the temperature contour which is available from the simulation. In the simulation you have got all parameters essentially superimposed with the velocity vectors. You see, as this hydrogen jet is coming, now because of the pressure rise because of the pressure rise at the base, the jet penetration becomes limited, okay, into this recirculation zone. As a result, you see that there is not of course there is this large vortices being formed, but the jet as such does not penetrate immediately into the recirculation zone, and as a result of that, so here the jet can penetrate further downstream. Okay, so this this jet can this jet essentially penetrates up to this point, where essentially you have this recirculation zone also this entire flow recirculating, and this creates essentially a stagnation point. Okay, so this recirculation of the products which is formed here, and this whole jet essentially forms a stagnation point, and essentially you see that the flame is starting from here at this shape. Okay. So, the hydrogen jet, you see that what happens is that because of the pressure rise at the base of the wedge, this leads to a lower penetration of the jet into the recirculation zone. Okay. And the mixing region, as you see in this time averaged field, which is shown here, from here we can show that we can find that the jet has a rather low penetration, and these two vortices on each side of the jet only enhance the mixing of the hydrogen with the recirculating fluid. Okay. That is what is happening. So, this only these vortices that are being that are being present here mixes this hydrogen with the air, but as such in a normal recirculation zone you get hot products. So, here you do not see those things, here you just have fresh hydrogen mixing with the oncoming air which is coming here. Okay. And only further downstream the reaction and the volumetric expansion create a bubble with hot products, which is this thing, which is if you see here, only further downstream this recirculation of this bubble of these hot products form, and this create a bubble of hot products, and this circulation is imposed by the outer flow, which creates a reverse flow along the recirculation towards the injection. Okay. And thereby the flame is essentially initiated. So, this hydrogen jet essentially can penetrates up to this point, where it essentially meets this recirculating products, and that creates a stagnation zone from where the flame is essentially starting. Okay. And these recirculating hot products essentially provides energy, thermal energy to the flame, which essentially conducts upstream to essentially initiate the initiate reaction in the oncoming mixture. So, this is the dynamics of the strut, and as you see here of a strut stabilized scramjet flame, and as you see here that if we plot, if we extract the temperatures from different locations, the temperature profiles from different locations, and validate that from different locations from the simulation, and validate that with the experimental measurements, the experiments does correlate well with the simulations. Okay. So, it says provides some amount of confidence in the simulations, but then of course you have to one has to be very careful. These simulations are hard simulations, and there is a lot of effort that goes into modeling as well as in the algorithm development for these kinds of things. So, with that we have we come to the final some of this instantaneous temperature fields of how it looks like. So, as you see that because the flame is essentially stabilized here, and the recirculation bubble is essentially formed here, you see that in the instantaneous picture also, where you see that the flame is essentially lifted up from the bluff body, unlike the case of like subsonic flames, where the flame is essentially attached to the bluff body. Okay. Or here the flame is essentially lifted up from the strut, and that is happening because as the jet is penetrating into this, it meets with the recirculating products somewhere around, and that creates a stagnation zone, and that becomes the stabilization location of the flame. But occasionally this flame structure that is formed due to the some low velocity regions can occasionally penetrate, and it can get attached, but normally it is lifted up from the recirculation zone, and from the recirculation zone immediately downstream of the strut, and it forms its own recirculation zone downstream, which recirculates the hot products. Okay. So, this is typically the structure of the flame as you encounter in a scramjet combustor. So, with that we come to the end of this discussion on scramjets, where we have essentially discussed one dimensional flow, one dimensional frictionless flow in a constant cross section with heat addition. Okay, and we have seen that the addition of heat, what happens to is that the addition of heat tries to make the Mach number of the flow to more and more towards sonic. So that is the most important consequence that we saw. And then we looked into the different design considerations of a scramjet engine. We looked into the different phenomena that involves in a scramjet engine, like what happens when you inject a gaseous fuel jet, what happens when you inject a liquid fuel jet, what are the different mixing mechanisms that takes place. And then we looked into the different ignition delay times, which is of the order of 1 milliseconds often, and is often comparable to the flow residence timescales. We looked into burning time, and then we looked into the different mechanisms of flame stabilization. We looked into the cavity based flame stabilization, and looked into the strut based flame stabilization, and we looked into how the different shock structure interacts with the recirculation zone and the shear layers, and how it is different for a non-reacting case versus a reacting case. And if you inject the hydrogens through a strut, how it changes the flame structure from a normal block body stabilized flames, and you can have a stable lifted flame, which is just a little bit further downstream of the strut than it is under normal circumstances of under different circumstances of subsonic flow, where you have a flame essentially attached to the strut. Okay, so we have discussed these things, fundamental aspects of combustion in scramjet engines, and with that the technical part of the course is over. We have come to the end of the technical part of the course, and we will finish it off in the next class with a recap of all the topics that we have covered in the last 12 weeks. So goodbye till then.